is the last ingredient for the statement of Stokes' theorem. And so after we understand this, we can finally use Stokes' theorem to compute some work of vector fields. In order to make this more concrete, before giving you the general formula, let's start with something that you actually already know the answer to. So imagine that I asked you to find the surface, the area of the surface of a cylinder. So imagine that you have here a cylinder of radius r and height h, and you want to find the area of excluding top and bottom. So you just care about like the lateral part of the cylinder. So another way to say this is that here I have a cylinder of radius r and some height h, and I want to know the area of this cylinder. So notice that here there's even no top or bottom, so we're excluding those pieces. And well, the reason why I say that you already know the answer is that basically you can do what I just did. You can imagine cutting open the cylinder, and when you open it, you get a rectangle, and so you get that the area should be, you get a rectangle of piece of paper of height h and length 2 pi r, so the area should be 2 pi r h. Okay, and so we will get this area back. The point of view that we want to take is that you have to imagine that the cylinder is made out of tiny pieces of which are basic. Well, in this case are like rectangular, really, but in general they're just like they're not like necessarily flat. So basically, I'm trying to draw rectangles like this. And so these are the ones that are making up all the area. And so if we find the formula for the area of these tiny rectangles, by adding them together, you get the total area. Okay? And so what we need to do is like, we have to say that the area, let's say each of these pieces of cylinder has some area. Usually when it was a double integral, right, I would write dA. Now I want to write ds because you think of it as a surface. So and like the point is that all the area of our surface, this is like in general, it like applies not only to the cylinder. The area of a surface should be an integral of all these pieces ds. Okay? You draw all these tiny rectangles over the surface and you add them all together. The point is that you cannot really add them in the strict literal sense of the word, because you have to imagine that you're shrinking the sizes so that it becomes a better and better approximation. And before writing, so what we need is a formula for ds. Right? Remember that, for example, in the case of polar coordinate, in the case of double integrals, ds was really dA, and dA was like dy dx or r dr d theta, and so we want like a general expression. So let me do it first in the case of a cylinder, and then I'll give you the formula. So what you need to do to find ds is we need to parametrize the cylinder. And so what do I mean by parameterize a cylinder? This means that you have to specify every point on the cylinder with two numbers. So write the position vector of a point on the cylinder with two numbers. So the idea, just to make an analogy, is that when we have a curve, right, we said that the position vector of a curve, right, if you think of it as a trajectory of a particle, the position vector of the curve at any point was like a function of time, right, because at any time the particle has to be somewhere. So we wrote every point on the curve as a function of time. And that's how we thought about curves in general. Now the point is when you have a surface, not just a cylinder, but like a general surface, well, you don't, it is not enough to specify a point on the surface with just one number. That only happens for curves. What you can do is, again, specify the position vector, but instead of using one number, you have to use two numbers, which we call u and v. And so the idea is that any point on the surface will be a function of these two numbers. So you think of it as x of uv, y of uv, and z of uv. And again, just to make this concrete, let's try to think about what the case of a cylinder looks like, what a parameterization for the cylinder will be. Let me draw this again. Let's introduce a coordinate system. Let's say our cylinder starts at the ground level, so it begins on the xy plane, and so it has height h, and this is a circle of radius r. Right, so the points on the cylinder, the equation of a cylinder is x squared plus y squared equals r squared. Well, you would say, isn't this the equation of a circle? Yes, that's the equation of a circle when you just think about the xy plane. But when you think of this equation on xyz space, this gives you no constraints on the third coordinate. So that means that z can be anything that you want. Or another way to think about it is that you take the circle and you slide it off along the z-axis, and that's how you get the cylinder. Okay? Let's call this radius r so that it's not confused with the, so that it looks more like a fixed quantity. And so the idea of a parametrization is that you would take a point on the cylinder, which is of the form x, y, z. Any point in space has three coordinates, but because it lives on the surface of the cylinder, you can kill one of the coordinates, or make the three coordinates a function of two coordinates. Okay? And which are those coordinates that you can use? Well, in this case, you can use cylindrical coordinates because we're working on a cylinder. And notice that in cylindrical coordinates, right, the equation of a cylinder becomes r squared equals big R squared, or r equals big R. So what that means is that when you live on the cylinder, right, if you're on the surface of a cylinder, your radius cannot be arbitrarily large because you're fixing the radius. And so what this is saying is that any point on the cylinder x, y, z, in principle is of this form: r cosine of theta, r sine of theta, comma z. But the r is not whatever you want. It's not free. So this is not free. And so R is bound to be big R. So that means that the only two variables that are free to change along the surface of the cylinder is z, and that makes sense because you're allowed to move a point vertically along the z-axis, and you're also allowed to rotate a point. So you can move you can change the angle of a point, but you cannot change the distance of a point to the z-axis. That's what this is saying. And so what this really says is that this is actually like a parametrization of the cylinder in terms of theta and z. So you can think of x as a function of theta and z, which is r cosine of theta. Then you can think of y as a function of theta, z, which is r sine of theta. And then you can think of z as a function of c and theta, which is just c or z. And so the position vector, what I'm like the point here is that well, let me do it on this side. The point is that the position vector on the cylinder, right? The position vector here of the cylinder is really a function of two variables, and it gives you that expression. Okay, so I haven't explained why we cared about finding this parametrization. Again, what we're trying to do is find the area of these little rectangles. But in general, you should expect this is like an accident because we're working on a cylinder, so they really look like rectangles. In general, they look more like parallelograms. And so when you have a parallelogram, remember that you can find the area of a parallelogram by taking the cross product of the two vectors that make the parallelogram. So basically, I'm trying to find this piece of area, the S, and I'm saying, oh, we just need to know what these two vectors are, and then you take their cross product. And so the thing is, like, from this equation, you can find the two vectors. So let's think about that for a second. Let me draw the cylinder here one more time. And so the partial of r with respect to theta we're going to generate two new vectors out of this. And so what would this be? Again, this means fix the height of the position vector, right? You're going to, this is a partial derivative with respect to theta, so z is fixed. So you fix the height at which you're looking this position vector, and you only vary it along the theta axis. So you're going to vary it along this pin curve, and you actually get like a velocity vector because you fixed one of the variables. So you're going to get like a velocity vector, which is this one, which is tangent to this pin curve. And so this is minus r sine of theta, r cosine of theta, 0. And so what I'm trying to say is that if you fix some height, you get this vector, which is this unit vector. Well, not necessarily unit vector, but you get this tangent vector, which is moving. Okay? And likewise, if you take the partial derivative of r with respect to z, then you get 0, 0, 1. And this one makes sense because you're fixing the angle. So imagine that you're fixing this angle and you're just letting z vary. So if you just let z vary, you're just changing in this direction, and so the velocity vector, you get a curve on the cylinder, which is here. And what I'm saying is that in this case, the velocity of this curve has to do with this partial derivative with respect to z. But surprise, surprise, here we have our desired parallelogram. So the idea is that we got naturally like a parallelogram here made out of these two vectors. So, and this is the actual formula, which I'll remind you in a second. But this piece of area, this tiny parallelogram, which has some area ds, can always be computed, well, in this case, can be computed as the norm. Remember that the area of a parallelogram is the norm of the cross product. Well, it doesn't matter in which order you write them, because this is, we're going to take norms. And the idea is that something similar will happen in the general case. Okay, so really this is the formula for the tiny piece of area on this side. Remember, like strictly speaking, like dA always has like either dx, dy, or dr, d theta. So strictly speaking, like you have to multiply this by dc, d theta. So that before I forget about saying that. But so let's see how this looks like in this particular case. Let's do this cross product somewhere in here. So we're trying to take, well, we have to do the cross product first and then take it as the norm. So the cross product is minus r sine of theta, r cosine of theta, 0, 0, 0, 1, right? Let's just put it here first. And so this is the, again, this is not too bad. This is r cosine. This becomes r sine. And the other one gives you 0. Okay? So really ds is the norm of r cosine theta, r sine theta, 0, dc d theta. And then, well, this is root of r squared cosine squared plus r squared sine squared. So once you take r squared from the square root, you just get r. So ds equals r dz d theta. Okay? And so, how is this going to be useful? Because remember that the total area of the cylinder, right, or any surface, I said, the area of any surface is the integral over the surface of these pieces ds. In this particular case, it would be the integral over the surface of r dc d theta. Well, what are the values for theta? Well, theta has to go from 0 to 2 pi. And what are the values for z? Z goes, well, remember it had height h. I just it started here on the xy plane, so it goes from 0 to h, for example. And so this would be r is constant, is a cylinder of fixed radius r. So you just get an integral from 0 to 2 pi, 0 to h of dc d theta. These are easy to integrate because they're non-functions, so you just get h times 2 pi, so you get 2 pi r h, which was the same formula that I did before when I cut open the cylinder. And so in general, let me write the, and this is the thing that we'll start using next time for Stokes' theorem. In general, you'll have the surface again, the position vector of the surface is a function now of two variables, u and v. And again, like you can generate like a tiny parallelogram on this surface by taking the partial derivatives with respect to each of these variables, which are sometimes called parameters. And the main formula that we have to know from this video is that this piece of area, you get like a tiny parallelogram where one of the sides is dr du, one of the other sides is the r dv. And the point of this formula is that the piece of area is this thing. And notice that this is, by the way, something that we will use later also, is that remember that with the cross product, if you don't take the norm, but you just make the cross product, you get a vector that's perpendicular to the surface. And so this will be another way to get the normal vector. It's just that we have to rescale it so that it becomes a unit norm. But that's not entirely important right now. The important thing to remember from this video is this formula. So next video, I'll start applying Stokes' theorem to compute work, and in order to use Stokes' theorem, we'll have to do integrals, which require first making this parametrization of the surface.